lamps and multiplexers and sync separators and all those little things that come in a silicon package. And while doing that, the first company I was at was a Lantec, which has gone now. It's now called Intersil. But I was designing television parts and that. One of the guys came to me one day and he says, "Kevin, the people in Korea are buying lots of these buffer amplifiers and operational amplifiers. We don't understand why they need them and what it's for. They say they're using them for gamma correction. What do you know about gamma correction? You're a television guy." So anyhow, I went off and talked to the Koreans. It was mostly the Koreans in those days. It was the days of 10, 12, 16-inch LCDs, and they were just getting out of the laptop kind of application and starting to try and put pictures on them. So off I went to see what they were doing. Sure enough, yes, they were doing gamma correction, and I'll just refresh your memory for the people who, particularly those who grew up in the digital era. But gamma correction, a lot of what's going on in television for gamma correction is as a result of having a CRT at the end of the chain. So the CRT doesn't have a linear transfer curve. The beam current is hitting the phosphors and making the brightness, and it's not a non-linear process, which is a lot of people believed when I got into this. But the beam current provides a linear translation into brightness. The non-linear bit, though, is the grid, which is controlling the number of electrons going down the tube. And it's normally a square law. It's maybe not quite square law, but the numbers are around about 2.2 to 2.4. So the output is the input raised to 2.2 or whatever. And that number is the gamma value of the image. So that started the need for gamma correction, because what you really want is, from the original scene where you've got brightness values going between black and white, you'd like the output, the viewer's eyes, to see the same kind of representation, black to white. But you've got this picture tube in there, so it's going to take a linear signal and modify it. So somewhere in the chain you need something to put that right. So you need to read what we always knew of as gamma correction back in the camera. So back at the studio, or particularly in the camera usually, was this gamma corrector. And all of us who've worked with cameras with linear transducers in them have all come across gamma correctors in the past. Those of you who only played with Vidicons may not have found it. The Vidicon happens to have about that kind of characteristic, and it kind of works. Good enough. So that's the reason for needing gamma correction somewhere along the line. But the LCD manufacturers, actually, the part that they're going to need this strange curve typically was the power supply board. And so you got some poor power supply engineer, and I don't know over here, but typically the power supply engineers are the new guys on the block. So they didn't know anything about television signals and gamma, but they were told they got to do the gamma correction because it was a non-linear function. So originally you got a monitor which has a strange transfer characteristic. The camera has a gamma corrector in it. So there's two complementary curves. And the monitor didn't need gamma correction because that was what was causing this need. Now we've got LCDs. They're not the same as a CRT. They're going to do something different. Well, an LCD, and this can get really drawn out, take 4 hours or something. So what we're doing here is we have light, unpolarized light, and there is a polarizer. This is a cross section through an LCD. There is a polarizer, a light polarizer. So the light comes through the polarizer, and in this case it's only in that direction, the light coming out. And then we have the LCD pixel, if you like, and the light at the other side, there's another polarizer Now if we left it at that, if that light came straight down to there, it would be blocked by the second polarizer because it's at 90 degrees. So there would be no light coming out at all. However, we've now got the liquid crystal cell, the pixel itself. And what they've got is the liquid crystal material is in there, and they put a twist on it. So between the top surface and the bottom surface, the crystals are aligned so they're gradually moving round like that. And that rotates the light polarization with it. So in this case, the light, which is that polarization, will be rotated so that it's in line with the polarizer at the bottom. So the light will pass through the second polarizer. By the way, the way they get these things to line up like that is they scratch the surface. It's shown as a zigzag there. They scratch the surface. It's kind of a crude term, but they talk about using the rabbit's fur rollers because it looks like rabbit's fur, and these rollers run round and they scratch the surface of the material. So molecular force causes these things to sit in this manner when they're not touched. If we put a voltage across it, across the cell, it attracts these liquid crystal molecules and it aligns them in a different orientation. And so by changing the orientation, now the light doesn't get rotated like it did there, and so it gets blocked. So this is with no voltage across and with a voltage across. So we can change the transmission through the LCD cell. And in this one, they call it normally white because we've got white light coming out when there's nothing happening. So it's normally white. Of course, if we rotated one of these polarizers, it would be normally black. So there's a couple of variations on how you make this. And it shows an AC signal there. That's a little tricky. We'll get back to that. You just need to put a voltage across and attract these molecules and get them to line up. So because there's rotation involved, as you might guess, there's some tricky number involved. There's sort of cosines and sines involved. So the actual transmission curve, this is the normally white one. So with no voltage across, we get 100% transmission. But as we change the voltage, we gradually reduce the amount of light passing through the cell. But it's not very linear. So we've got another problem. It's not like a CRT, it's different. It's got this S-curve to it somewhat. And then on top of that, by the way, if you're going to use an LCD in a television system, where most of the viewers, back 15 years ago, most of the viewers were still using CRTs. So obviously the gamma has been applied back at the studio. So the TV signal is already gamma corrected. And now we've got double trouble because we've got this strange transmission characteristic as well. So two solutions. One way is, let's make the signal going into the device, let's make it non-linear, and then we can have a linear D to A converter. We need an analog voltage, remember, we're getting back to analog finally at the end of the chain. And then we could make this thing look like a gamma corrected TV signal. Or we could have a linear data, so it's just a straight 0 through whatever the top count is of the data, and a non-linear DAC, and then we get the same result. So we've got to get this non-linear in there somewhere. And by the way, back when this all started getting rolling, building these DACs is not that simple, and so they typically were 6-bit DACs. So even though this was television, it was using 6-bit DACs. So a whole LCD screen is going to need lots of these little pixels. It's going to need, nowadays it typically needs 1080 rows of pixels and 1920 columns of pixels to make up a full HD TV. So we've actually got to address these pixels, and typically what it is the horizontal rows going across, and all these little transistors, thin film transistors, hence TFT LCD. So all these little transistors, the gates are all connected into these horizontal rows. So we can bang that horizontal row with a big voltage, turn all the gates on these transistors, and then the vertical rows, which carry the actual signal needed to manipulate the pixel, we could put a voltage on the Y signal there, and it would go through the source and out to the drain, and it'd be applied across this liquid crystal. There's a liquid crystal, which by the way has got some capacitance on it. So once we've applied that voltage, we can turn off the transistor and the voltage will remain across the liquid crystal, purely due to the capacitance on it. It's not really enough actually. This is a more detailed one which I won't hover over too long, but they typically add in, besides the liquid crystal, they add in a real capacitor which is deposited on the glass with a metal film, and so it gets a little more complicated. Storage capacitor plus the liquid crystal, and then we've got the gate drive in the horizontals, and the drains are being driven by the verticals, the sources rather. This is data. So required curve, just going back and looking again, 0 through 255 if it was an 8-bit system, and this is probably, they use the term nits a lot in LCDs. 250 was a typical value. I think it translates to candelas per square meter. So 250 is fairly good. 300, 400 makes a nice bright display nowadays, and that's pretty easy to achieve. Unfortunately, of course, remembering back to this twisting motion, we don't have a linear one, we have this kind of curve. So if you didn't do anything, the LCD curve would look more like that. And that really is, that's a bunch of numbers in a spreadsheet and plotted, and those were taken off of a real LCD. So if I'm going to correct it using a DAC that's non-linear, the output of the DAC has to be a reverse of that curve. So this is the required curve of the DAC. So it's not your usual 50% is 50% out, so on. It's a non-linear DAC. By the way, I'm thinking about it, across the top of the LCD screen we've got 5,760 DACs, each one driving a vertical column. So these chips that are sitting on the top of an LCD screen, they're pretty significant design work. So there's a monitor. I took a monitor and I plotted it. These are real values, plotted the monitor, and it looks just like the textbooks say. It looks like a monitor curve. And there's an LCD plotted against a CRT monitor. So that one wasn't too bad. That one's had some corrections applied, obviously. So inside the LCD, and this is kind of old now, they keep putting things closer and closer together, and they really only want to have one printed circuit board to keep the cost down and so on. But earlier on there was a separate board with the DC to DC converters, and it generated some reference voltages for the DACs and so on. We had what they call a TCON board, timing controller is what that means. And that generated all the digital pulsars and brought in the digital signal and translated levels and so on. DC to AC converter for the backlight. And then the gate driver ICs, those were the ones that turned on the horizontal rows. So typically that was driving a 0 to 18 volt signal to turn those transistors on good and hard. So they're just switches really. And then the source driver chips, multiple ones of those, because you can only get so many pins on one chip. You've got 5,700 and something of these D to A converters. So there's 5,700 and something wires going onto the LCD panel. And quite a significant development cost of these source driver chips. You know, the mask set, the equivalent of the negatives when you're making a printed circuit board, a mask set for one of these chips could easily run a couple of $1 million. So you don't want to be changing them too often. So this D to A converter, they're very simple type of D to A converters. We've got a lot to build, so we want to make them fairly simple. So what they do is they have a resistor string. So now we've got lots and lots of voltages. Here I'm showing a 6-bit system. So we've got lots of voltages, they're buffered with little amplifiers, and then off they go to a switch. And so by putting a digital signal on here, we can select which of these DC voltages we send down that column for that particular write. And of course I don't have to have equal value resistors. If I make these resistors all different values, now I can get that non-linear curve. The problem is that from month to month the mix of LCD material wasn't the same. It came out slightly different. Manufacturing tolerances of printing these LCD panels, all the wiring, overlaps, crosstalk on the capacitances, meant that from month to month the gamma kept changing. You know, and that was okay in the first days of laptops and no pictures on them. But as they started using them more and more for television, they had to have a way of tweaking the gamma to get it a little bit closer to what they required. So what they did is they put another resistor chain, here's the DAC resistors, they put another resistor chain outside of all these complex circuits, and it was common to all of the DACs across the panel. And now all we had to do is change this one set of resistors externally, and it wasn't as many resistors either, it was only the tap points going down here, so they chose a few tap points. Change those resistors and we can modify the gamma on a month-to-month basis as needed. By the way, nowadays they do it for every panel. They put a light meter in the front of the panel, they go through the range, it monitors them, and it goes in and it changes the resistors. It doesn't actually change the resistors, you'll see in a minute, which is where I came in. So when I came in, this is where they were using these high-speed buffer amplifiers, because there's a lot of switches out here and they're all going to connect at once, and then on the next line the voltage may be different, so they'll connect to a different tap point. So there's this big load of capacitance going onto this reference voltage and it pulls it away from the reference voltage. So the op-amps had to be quite quick, have a fairly high current capability. These were typically 5-10 milliamps peak, but they had to provide a little bit more than that because they needed to get all the stray capacitance out here charged up or discharged quickly. And something I don't show you there, there's another amplifier in there which is the common point for all the capacitors out on the screen, and they call that VCOM. And that one, nowadays it can typically require 1.5 amps on it to charge these things fast. So we had the curve there. Once again, we're still on the 6-bit system here to make it simpler, but we had a curve, and potentially we might want to pull these tap points up or down to modify the curve. So by having that resistor chain we could do that, but that was tedious as well. So what they did is we were approached by, I think, Samsung originally, and they said we want to be able to do this automatically. So originally we built these little amplifiers and they fed onto the DACS. So there was a bunch of amplifiers, but instead of playing with the resistor values going into the amplifiers, I'd changed company by then, I'd gone to Maxim when I did this drawing. I worked for Lantec and then Maxim and then another company after that even. So what we did is we built some more D2A converters that go in there, and they can read from memory and apply a voltage to the input of these buffers. So now you didn't have to go in and tweak all the resistors for the gamma points. You could go in through an SPI or an I2C bus, and you could put a value into the registers and set these curves. And probably I should mention at this point, you notice there's a set there and another set there. When I told you that we put a DC voltage across an LCD, if you keep doing that on a continuous basis, just like a CRT, it starts to burn in, believe it or not. So what happens is you get a kind of a plating action going on. Impurities start moving around in the liquid crystal material itself. So to prevent that, what they do is they put a positive voltage on the LCD, say one frame, and then the next frame, let's turn it over and put the same voltage in the opposite direction. Not quite that simple, but that'll do for now. It gets complicated. They do it pixel by pixel or 3 pixels by 3 pixels and so on. But we do have to invert the polarity on a repeating basis. So the easy way to do that was we had upper voltages which went from a fixed voltage upwards. We had a set of lower voltages which went from the fixed voltage downwards. It doubled the voltage range needed, but it was the easiest solution. So that was one of the challenges as well, by the way, that now we need about 16 volt range on here, and 16 volts is it's kind of the limit of one of the silicon processors, and the next step up is 22, 23 volts. So it kind of set it at that, because as you go up in voltage, the number of layers you need in the IC goes up and the cost goes up. They don't want to pay anything for this stuff to put in these TVs. This chip sold for about $5 to start with, and they beat on us and they reverse engineered it to see how much silicon was in there and calculated how much it would cost and figured out what our profit margin should be, and they beat us down to $1, and I think when I left this company it was down to about 80 cents. So you're getting a whole bunch of D to A converters and a bunch of memory and another little converter there, all of that for about 85 cents or so. And there it shows that we have this sort of split range. We can generate voltages from there to there or from there to there to correct these D to A curves and generate a voltage in the middle, the one that took quite a bit of current on these big screens. These huge screens that we see nowadays, the size of this, that's where you need this going up towards 1.5 amps, because you've got thousands of capacitors on the other side of this common connection. I'll jump topics. I just threw this one in a little bit. I kind of just brushed the surface of what's going on in terms of the analog process to the pixels. I then moved to another company where I was doing different things at this company, but it was a company, Atmel. You probably know it from the Arduino chip, but Atmel is a microprocessor company, and we did some LED drivers, so it optimized the voltages to get the right currents through LEDs. And one of the things we did for various companies, they wanted to be able to control the backlight of an LCD. So instead of just having a strip, although that works as well, 10 years ago, 8 years ago, people were getting into where they were changing the brightness of the backlight by zones, because an LCD only has a limited contrast ratio, and the marketing thing was who can beat who with the contrast ratio. 1,000 to 1 didn't sound very good, so the marketing guy wants 1,000,000 to 1. So how can you get 1,000,000 to 1 if the liquid crystal display's only got 1,000 to 1, and that's pushing it. To get a more of a contrast ratio, what you can do is you can look for the dark areas on the LCD and you can dim them down. So we did zone backlighting, and this was one way. Now this slide actually is prepared, you notice zone 1 is all of the top there pretty much, string 1 is zone 1. So we could do it individually and dim and bright parts of the picture. I think it looks ugly. You get a bright pinpoint on the screen and it's got a halo around it because there's not as many LEDs as there is pixels, so something's got to give. It's a coarse resolution of brightness control. But another thing occurred about this time. LCDs were getting quite good at picture displays now, and the contrast ratio was kind of adequate and the gamma was pretty good now, But one of the problems was the blurring. If you remember, the original LCDs were really bad. You had to have what was called mouse trails, because every time you moved the mouse you couldn't see where the cursor had gone. So much later on it was pretty good, you could see the cursor, but people started to notice that moving images, fast moving images, sports and so on, they were blurring the image. So people started to increase the field rate on LCDs. 60 Hertz was no longer the in thing, 50 Hertz for you guys. So everybody wanted 100 Hertz. Now it's 200 Hertz frame rate. I think it's a bit of a scam, but anyhow, that's what they did, because if the data's coming in at a slower rate, it's not going to look that much better. But one of the problems is the LCD itself blurs the image, because it takes a while to change this stuff. There is a bit of a time constant charging up the capacitance when we write to the pixel. But even worse is this liquid crystal material. If you think of it like treacle, it takes a little while to settle into the right shape. So what was happening is, if you write it, this is vertical sync, so this is one field of a picture from there to there. So if at the top of the screen, row 1, that very top row of pixels, if you write to those, and assuming you charge them up instantaneously pretty much, it takes a while before they settle, the twist settles into the correct position. So if I drew a curve of that, it's going to take a little while to settle. It doesn't actually settle until, maybe halfway down the screen. So all the time, if I'm illuminating it during this time, I'm illuminating the wrong brightness values. So it would be nice to wait for down here. So what we did is we divided up the screen into strips, because you can't afford to have a strip of LEDs for every row on the picture. So you take a bunch of them and say, okay, that's the top row, and in this case I got 135 rows of pixels being illuminated by one row of LEDs. So the first one obviously starts settling as soon as it's written to. The last one in that block is going to be a little later. So now I know that I've got to be somewhere in there, this time period here. If I illuminate it then, I'm illuminating settled pixels. I'm not illuminating the screen continuously, I'm doing it by a time factor. So now we're moving into a new dimension where they're blinking the backlight so that it optimizes the pixels that should be illuminated. And remember this curve here. One of the things we want to do is they want to change the brightness as well. According to, if it's a dark scene, they'll reduce the backlight. If it's a bright scene, they'll increase the brightness of the backlight. And you do that with LEDs by varying the time that the LED is turned on. So now we can start varying the length of time. Obviously, if you lengthen it too much, now you're back into illuminating it while the values are changing. So there's a lot of little tricks played to find the absolutely correct time to illuminate the pixels. And you end up with, you've divided the screen up into multiple zones, and consequently the lighting period for each of those zones is also staggered. And this is what's called a scrolling backlight. And Philips were probably the first ones to come up with this, and they actually did it with the fluorescent backlights to start with. So they were switching the fluorescent backlights and scrolling them down the screen, and that allowed the pixels to settle, and you weren't illuminating settling pixels which blurred the image a lot. Obviously much better on those. There is an article out there on ECN magazine. There's also one in which goes into that in much more detail, because I'm just brushing the surface. And even then it doesn't go in a lot of detail. I wrote the article for Sony to explain how to do a certain thing for Sony. And a marketing guy took it and reduced it down to about 10% and put it in the magazines after I'd left that particular company. But there is a little more description on how that scrolling is achieved in there. And by the way, I'm also a collector of cameras, like Brian there. So I thought I'd just show you some of my cameras. I was getting ready to move them in, and I'm proud that I've got some British cameras in there. A couple of Emmys. There's a Pi camera back there. There's another Pi camera somewhere else on a trolley, I think. So I'm also a camera collector. One day I'll get this website going correctly, but probably each page will say refer to Brian's website, because it's got to be the website for cameras. And then just finally, I was in Finningley once before. I used to cycle to Finningley to watch the Vulcans, and then one year they had an air show, and I cycled up and spent my pocket money to have my photograph taken in an airplane. I happened to find that the other day. I thought, well, that's kind of fitting for him.
What was the aircraft?
I don't know. It was only a cockpit. There wasn't much more of an aircraft. But, and those were the days when you could cycle up and lean your bike against the fence and come back to it afterwards. So I kind of brushed the surface of it, but LCDs are much more complicated than they look. By the way, the 6 bits went to 7, to 8. Mostly they're 8 bits now. And it's very hard to do a gamma correction in the digital domain because you just haven't got the fineness of correction if you try to do it with an 8-bit DAC, because the curves are very flat in places, so you can't get, it's just too big a jump between values. There are some 10-bit LCDs around. Some of them are 10-bit linear. Now you can start to do the gamma correction back in the digital processing. So sometimes you'll get an LCD monitor and it's got a gamma adjustment. It goes in and adjusts these points on the curves.
Excellent. Thank you very much, Kevin. That was actually very, very interesting. It was really good. So thank you. Thank you. Yeah, very different. It's good. I'm glad to see Brian's got competition for the Camry Museum. Okay, so it's lunchtime. We're a little bit late, but I think we need to finish on time. So we come back at 1:30 for the final 2 sessions, one of which will be Charles on Skype, and then we'll have Chris back again to talk about vMix.